Well, let me tell you about one other that we're going to work with today, and this is the one you probably have not heard of, and then you might ask, why are we working with it? And I'll tell you why. So this is called the Chebychev polynomials. Just like all those others, they're just special functions. And let me write down the Chebychev differential equation. Okay? Here it is. We have 1 minus x squared out front, d dx, square root 1 minus x squared. Second derivative here, plus n squared t of n is equal to 0. And it's on the domain -1 to 1. And you, of course, may ask, how could this possibly help me? Okay, and that's what we're going to address today. So first of all, it seems a rather esoteric thing. So maybe you've heard of the Chebychev polynomials. Maybe you haven't. They're just like any other special function. But there is a difference between it. And the only reason we're going to talk about it in class today and why it becomes sort of more prominent than the other special functions is because this in particular can get fast. I can do that transform in n log n. There's very few special functions that you can get n log n speed out of, and this is one of them. Okay? Couple things to note. First, this is a Sturm-Liouville form. And if that doesn't mean anything to you, let me tell you what Sturm-Liouville means to me. When I hear Sturm-Liouville, what I think of is eigenvalues are real and distinct. Eigenfunctions are real. You have orthogonality. It's a complete set. There's all these amazing properties when you say something is Sturm-Liouville. It's the same as saying a matrix A is Hermitian or symmetric or self-adjoint. All these properties happen when you say words like this. There's all these amazing things about the eigenvalue structures, about the eigenfunction structures. All that means is special matrix. In fact, I think from the ancient German, Sturm means special, Liouville function. I know that because I am a scholar. Okay, anybody buying that? No? Okay, good. All right. I think there are two dudes who worked on this. So first of all, the eigenvalues are real. And they are just n squared. Those are my eigenvalues. So remember, when we did the Gauss-Hermite, we found the eigenvalues were 2n minus 1. So your eigenvalues were 1, 3, 5, 7, 9, so forth. And here, they just go like n squared, right? 1, 4, 9, 16, 25, all the way up. Okay? Those are your solutions, or your eigenvalues. The eigenfunctions are real. I'm going to show you what they look like in a minute. T of nx. These eigenfunctions are also orthogonal. What does that mean? That means when I take an inner product against T of n versus T of m with a certain weighting, there's 0 if n is different than m, and non-zero if n is equal to m. Okay? So this is a lot like a coordinate basis. When we think about orthogonality and x, y, z, right? You think of x, y, z being orthogonal. Why? Because, in fact, if I take the inner product between x and y, inner product is just the dot product, it's 0, because they're in different directions. So in a vector space, I can represent any point as a combination of x, y, and z. Uniquely, because they are orthogonal. Same thing happens here in function space. You live now in function space, and I can define any function as a sum of these T of n, where they're all orthogonal. So instead of going somewhere in a distance in a vector space, you're going a distance in a function space. Okay, yeah?
That's not the case with the Bessel.
No, that's true for all of these. Yeah, in fact, all of these. In fact, when you did the cosines and sines, what the FFT is really doing is give me a function and tell me how much distance or how much cosine 1x or cosine 2x do I have? And cosine 1x and cosine 2x are orthogonal to each other. So they're like a vector. It's a generalization of a vector space. It's a function space. So you have this idea that not only do you have orthogonality, but also what Sturm-Liouville guarantees for you is it has a complete basis. And what a complete basis means is I can take any function and I can represent it guaranteed by this t of n, a sum of t of n's. Okay? That's what Sturm-Liouville means to me. Nice function. That is the bottom line about all this stuff. Sturm-Liouville really means nice. Where that's sort of not a well-defined term, except for you know nice when you see nice. Right? We know that about people, too. Oh, that's a nice person. Nice. Okay? All right, so how do we define these t of n's? Let me show you that. Because we're going to make the claim now is we're going to expand everything in t of n's. That's going to be the bottom line of what we do with Chebychev polynomials. Is we're going to say, give me a function, write them in terms of these t of n's, and I got n log n speed to work with. Okay? So here's how you define them. I'm actually not defining it in terms of x here. We'll get back to that in a minute. But in terms of cosine theta. T of n cosine theta is cosine n theta. So let's talk about T0. T0 would be where n0 is in there. So this is your cosine theta. And then this would be cosine 0 times theta. Cosine of 0 is 1. Okay? And I'm going to say that, well, basically, I'm going to work with x is equal to cosine theta. So what you find out here, then, is that T naught of x is equal to 1. Okay? What about T1? T1, this is going to be cosine 1 theta. But cosine theta is equal to x, is it not? Right there. So this becomes x. Then I have T2. Probably the best of the movies. T2 was, I don't think. Do you think? Yeah? Anyway, I thought so. T2? Anybody vote for that? T2 is the best one out of the Terminator series? When I say T2, that's what I'm talking about. No? Okay. All right. Sorry. Sometimes I say things. I'm assuming you're with me. But I've noticed that sometimes my popular culture is a little further ahead than most. So I shouldn't brag about that, but I do on occasion. Okay. Cosine 2 theta. You can always write, right? There's this. Remember my 3.5 by 5 trig card that I told you about? This is where it comes in handy, because cosine 2 theta can be written as, is it what, 1 minus cosine squared theta over 2? Do you remember that? Something like that? You can write that, something like that. Well, when you do that, now you have it back in terms of cosine theta, which then allows you to write this as this. Then you're going to have a cosine 3 theta, which you can always write in terms of cosine thetas with an appropriate expansion of what the cosine triple angle is. I did not have any cosine triple angle formulas on my card. I did not need that in high school. Okay. I needed many things, but not that. Okay. Let me just write a few more of these things. Okay. So a couple things to notice. So 1, x, and you can just keep going with these. Here are your basis functions. They're orthogonal to each other. That's what you're using. You're using these kind of interesting polynomials. Notice that even, odd, odd. You switch symmetry every other mode. Okay? And what do they look like? So they go from 1 to -1, and they are in the range from -1 to 1 on the axis. So T naught is just a constant. That's sort of like your DC component, if you will, that we had from before. That's T naught. So you remember, you're going to expand things in this interval from -1 to 1. Notice the difference here, by the way, between, we're going to notice the difference here, because we haven't talked about boundary conditions, but it's going to be important to figure out what the boundary conditions are if you're going to use these functions, right? Just like when you use FFTs, you're basically assuming you're using periodic boundary conditions, okay? That's implicit. T1 is just x. T2 is 2x squared minus 1. So at x equals 0, it's at -1. And when x is equal to 1 or -1, it's at 1. So at -1, 1, it goes, and it's a parabola like that. Okay? There's T2. T3 is a cubic. The cubic goes T3. I'm not even going to draw T4. T4 is a W. Okay? I should probably draw it because W is, we work at a place with a big giant W around there. Here. So T4. Okay. Anyway, now that I've drawn all those, you can't really tell what's what. But here's the point. Those are the eigenfunctions you're going to work with. You can expand everything. You give me a generic function from -1 to 1, and I'm going to say, I can write this thing down as an expansion like this. In particular, here's what I'm going to claim. I can take a generic function and expand in these special functions. Okay?